Let's now have a think about standing waves in air columns. For a pipe which is open at both ends, we're going to have antinodes at each end of the pipe. That is where the air can move freely at each end of the pipe. So if we had a pipe that was blocked at one end, then we'd have a node, but when it's open, we have an antinode, and the molecules of air move maximally around these points. So if we have maximum motion here and here, the length of the mode in this case would be half a wavelength. So we have half a wavelength here and half a wavelength here. So these would be the waves traveling in opposite directions, interfering to give this lowest order mode, which is for length L, half a wavelength. The next mode up would be a full wavelength. So in this case, the length of the pipe would be equal to the wavelength of this mode. The next mode up, so this is n equal to 1, n equal to 2, this is n equal to 3. In this case, we have 1 plus a half wavelength, so 3 lambda on 2 would fit into this length L. So in general, the length of the pipe must be some integer multiple of half wavelengths to have a standing wave in that pipe. Or in other words, the wavelength must be 2L on n. To find the frequencies of these modes, we use that the speed of the wave is lambda f, so the frequency must be equal to n times c on 2L, just substituting in the known value here for the wavelength. Now we can use this to calculate something. So for example, if we have an open pipe like this one, and we have the fundamental modes, that's n equal to 1, what length must the pipe have to have a frequency of that fundamental mode of 300 Hz? Well, for n equal to 1, frequency of 300 Hz, speed of sound about 350 meters per second, we can substitute these things in to find L. So L, rearranging this equation here, must be equal to c on 2f, and this gives us a length of about 0.59 meters. So standing waves in air columns are the basis for instruments like flutes, recorders, organs, all these sort of wind instruments. And when you excite modes in a system, you normally don't just excite a single mode. You excite a whole spectrum of modes that depends on the geometry of the instrument and the way you use it. So for example, when you blow across the top of a pipe, you might excite the lowest order mode, but you might excite some mixture, some superposition of these different modes. And it's the particular superposition supported by a given pipe or instrument that gives it its unique sound. As an exercise, you can consider a different kind of pipe, one that looks like this, where we have a closed end and an open end. So the fundamental mode in this case will be a quarter of a wavelength long, because we can satisfy a boundary condition here where we have a node and then an antinode at this end. The next mode along, where we have a node here and an antinode here, will have lambda on 2 plus lambda on 4, so it's 3/4 of a wavelength. And to get to the next mode, we add another half a wavelength, and then another half wavelength, and so on and so on. So what's the frequency of the nth mode in a pipe that's open at just one end? And that's an exercise for you guys. A really great example of the complexity of the mode spectrum that you can get from a system that looks a bit like a pipe is your voice box. So here you've got a bag of air, which is your lungs, and then your larynx, or your voice box, where the air passes through and we get some sort of resonant mode behavior. This is a video from YouTube of someone doing some overtone singing. Underneath, I've got an audio spectrum. So this is the frequency on the x-axis in hertz, in a logarithmic scale, and the y-axis is the power at each frequency, also in logarithmic scale. I'll have a bit of a listen to this video, and then I'll talk about what we can see on the spectrum.
Hello, I am Anna Maria, and I'm an overtone singer, and I'm going to tell you something about polyphonic singing today. Overtone singing is a voice technique where one person sings 2 notes at the same time.
Okay, I'm going to stop it there. What we have here is the fundamental frequency. That's the lowest frequency, so it's the mode with n equal to 1. It's got a frequency of about 270 Hz. The next one is at about double that frequency, and the next one is triple, 4 times, 5, 6, 7. So in the analysis that we looked at with the pipe that was open at both ends, it sort of meets this criteria. Each time we go to the next mode, the frequency goes up by adding the original frequency to it. So we have F, 2F, 3F, 4F, 5F, and so on. You can see these lower notes here don't really move around. What she's doing is something to the upper register over here. So we'll keep going. So if you look carefully, what you'll see is that these modes here are always kind of there. So you can see the modes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're always there, but she's moving her mouth around and enhancing some of these modes. So some of these modes enter her mouth and she changes the shape of her mouth to act as a filter, in fact, a resonant filter, so that some of these modes resonate with the shape of her mouth and enhance that frequency and suppress the other frequencies.
So this was the overtone scale on one fundamental. I can also choose an overtone and move the fundamental.
So this time around, she's changing the fundamental frequency. In that first set, she kept the fundamental frequency the same and then changed her mouth so that she chose to enhance or suppress different higher modes. Now she's moving the fundamental around.